Hello. I'm here to solve the two problems that you were assigned for homework. Three actually. These two problems, and then also the resonance homework problem in your packet. So I'll do the first two of the circular wave fronts in less than 5 minutes, and then I'll do the other problem in a short amount of time as well, hopefully 5 minutes. Alright, let's take a look. So, two identical point sources are generating waves with the same frequency and amplitude. The two sources are in phase with each other. Okay, so they're in phase with each other, so the two sources generate wave crests at the same instant. The distance between the two sources is equal to the wavelength, is equal to two wavelengths or two. Cool. So it shows it right here. So one wavelength is equal to two boxes, or 1/2 wavelength is equal to one box. Cool. Now we want to figure out where the waves from the two sources constructively interfere. So we know that according to the previous rule, wherever the path lengths are concurrent, wherever they arrive as an integer of 1 is wherever the difference in the path from point source 1 and point source 2 to any one of these points, wherever the difference is in multiple of one wavelength, that's where they're going to constructively interfere. Okay, so let's do it. We don't know which ones are constructively interfering, we just have to do some math to figure this out. Alright, so let's call this point source 1 and call this point source 2. Let's start with PDA. So source 1A minus source 2A is equal to 1 wavelength minus, this is one wavelength, from 3 wavelengths.
For B, this is 1/2 wavelength. Oh.
And then from source 2, that's 1, 2, 3, 4, 5, 6. Well, 1, 2, 3, 4, 5 boxes. So that's a negative 4 over 2, negative 2. Lambda. One, 2, 3. Now then, from point 2 to point C, things get a little bit tricky. But look at this. It's just a 3, 4, 5 triangle. So from 2 to C, we know that if this side is 1, 2, 3, and this side is 1, 2, 3, 4, the distance must be 5. 3, 4, 5 triangle, because that's a 3, 4, 5 triangle. Alright, so then from point source 2 to C, that is the length of the hypotenuse, that distance must be 5 boxes, or 5 over 2 wavelength, which is equal to negative 1 wavelength. From D, this is source 1D minus source 1 wavelength minus 1 wavelength, 0. Finally, point DE is equal to source 1D E is equal to source 2E. Oh, we have two more, not finally. So from E, that's 1, 2, 3. Source 2E is 1/2. Oh my gosh, this is 1 wavelength. These are all integers. This is the opposite of from 2 to C is 1 to F. So then I'm just going to steal this one. So I know it's 5 over 2 lambda minus 2 to F, which is 3 over 2. Every single one is a multiple of, well, all of them except for D are a multiple of 1. And if at point D, that means there's no distinction from the two sources. That means that they're meeting, the wave crests from point source 1 and point source 2 are meeting at D. The same waves are meeting at D. There's no difference in the distance between the waves from point source 1 versus point source 2. So not only are they in phase, they're also the same waves, or occurring at the same instant. All right. Yeah, it is all of them. All right, that was 5 minutes. Yikes. I'm gonna get this one done because they're all integers. Now let's look at this one. Wave sources separated by one wavelength. Okay. Now, two identical sources are generating waves with the same frequency and amplitude. The two sources are out of phase. Okay, interesting. So at the instant that one source is creating a crest, the other source is creating a trough. So this is out of phase. The wavelength is still equal to 2 boxes. And 1/2 of a wavelength is equal to 1 box. What's interesting about out of phase sources is that integers in this case are going to indicate destructive interference, not constructive interference. Half integers because in this case, if they're out of phase already, that means that if two waves are meeting at the same at the same point in their cycle, if the two sources are out of phase, then if one source is creating a trough and the other source is creating a crest, then there's clearly going to be destructive interference. The crest from one source is going to interfere with the trough from another source. However, if the two waves are, if one wave is meeting another wave at exactly half a cycle earlier, then you're going to get constructive interference because the crest from one wave is going to interfere with the trough of the other wave, or the crest of the other wave rather than the trough. Alright, so we want to figure out where constructive interference occurs, so we have to look for the half integers. So we still got to do a PDA. But now there's only 4, so this will be easy. PDB, PDC, PDD. I'll just set them all up in the beginning so it's easier. So source 1, I'm going to call this 1, 2. Source 1 to A is 1/2 wavelength, minus source 2 to A is 1, 2, 3. Source 1 to B, so that's half of a box, so that's 1/4 wavelength, minus from 2, that's 3/4 wavelength. Source 1 to C is 1, 2, 3, 4, 5. Source 2 to C is 1, 2, 3. Source 1 to D would be, well, let's see, from source 1 to D, that's well, what's interesting is that we know that D is going to be the same distance from both 1 and 2 because it's equidistant between 1 and 2, and so it doesn't really matter. We know that this is going to be equal to 0, even though we can do some algebra and figure out that this is 1, 2, so this has to be like, what, 5√2, 1 plus 2 squared is 4, 5, oh, square root of 5, what am I saying? But like, it doesn't matter, because even though this is the square root of 5, this distance from 1 to D and this distance from 2 to D, because the distance is the same, square root of 5 minus square root of 5 is equal to 0. Okay, now we see that if it's an integer, it must be destructive. So that doesn't work. That doesn't work. That doesn't work. So the only possible area where it can be constructive, if the two sources are out of phase, is B, because the two waves are generating the two sources are generating waves that are constructively interfering here, because while one source is generating, let's say, or one is generating a crust over here, point source 2 is generating a trough right over here. But then as they meet here, the crest from here intersects with a crest from this. This has become a crest. So then you have, that's not a good image of it, but it's the best I can do right now. Alright. That really wasn't a good explanation. Alright. Tuning fork is used to establish a standing wave in an open-ended pipe with an air temperature of 20 degrees Celsius where the speed of sound is 343 meters per second. Sound wave resonates at the third harmonic frequency of the pipe. This length of the pipe is 33 centimeters. That's labeled here. Third harmonic frequency of an open means that we have to label this, because it's open, the ends are going to be antinodes. And the thing we know about open is that the harmonics are going to be based off of the number of nodes. We'll say 1, 2, 3. Right, so okay, that's the third harmonic. Oh, that's ugly. Standing wave inside of it. So that's what we just did. Check. Determine the wavelength of the resonating sound wave. Alright, so based off of my understanding, I know that for the third harmonic, I could use a table, or I could just see right over here. There's 1.5 waves here. So, with that said, we know that the length is equal to 3 over 2 wavelength, right? The length here represents 3 over 1.5 waves. So the wavelength must be equal to 2 2 times L over 3. Is that consistent? So L is 33 centimeters, 66 centimeters over 3 is equal to 22 centimeters. Yep. .22 centimeters. Cool. The reason it has to be 22 centimeters is because this is one wavelength. Right? This is completing one wave. Well, actually, technically it's right over here. So it's approximately 2/3. This is one wavelength, right? Before it starts to go down again. So this is approximately the length of, ignore this part. This is approximately 2/3 the length of the entire tube. So the resonating sound wave wavelength. Determine the frequency of the tuning fork. Okay, so then to determine the frequency of the tuning fork, we know that V is equal to lambda times frequency. We know that the velocity is 343 meters per second, and we know that the wavelength is, oh, you can see my work, but the wavelength is 22 centimeters, so the frequency has to be V divided by the wavelength. In this case, V is 343, and the wavelength is going to be 22 centimeters or 0.22 meters. So then the frequency has to be cell phone calculator. You're not working as well as you should be. Oh, it should be 1559 hertz. which is in fact what we have here. Cool. Now, what is the next higher frequency that will resonate in this pipe? So in this pipe, if the length is limited, because it is in fact in this pipe we want to know, we would have to go up to the, we're at the 3rd harmonic frequency, we need to go up to the 4th harmonic frequency. To get it at a higher frequency, we need to go up a harmonic. So to go up, we need to go 4th harmonic. And at a 4th harmonic, we know we're going to have 4 nodes, and we know that we're going to have 4 over 2, that the L is going to be 4 over 2 times wavelength. So L is going to be actually equal to 2 times the wavelength, so the wavelength will be equal to L over 2. Now if we know that the wavelength will be equal to L over 2, because it's the 4th harmonic, we know that if L is going to be 33 centimeters, the L doesn't change. You always stay taking L's, Big Sean. You always stay taking L's. 33 centimeters divided by 2 is going to be equal to 16.5 centimeters. And if we have a wavelength of 16.5 centimeters and we don't want to know the frequency, we have to do this bad Larry again, because the speed of the sound doesn't change, right? It stays the same at a given temperature, and so the only thing that changes now is the oh my god, it's the frequency. And so the lambda is now, instead of 0.22, it's 0.165 meters. And that should confirm that our frequency will be approximately, 2079 hertz. The trick here is moving up the harmonic. Alright. And the problem that's in the back, you don't have to worry about that one just yet. Don't worry about this. We're going to talk about this in class, so don't do it. Alright. Cool.